I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, this is The Naked Scientists, the show that brings you the latest in science and technology and medicine. I'm Adam Murphy.
And I'm Chris Smith. This week we are meeting the neighbours, our planetary neighbours, that is. We're taking a look at Mars and Venus and the new missions that are heading their way.
Plus, in the news, COVID as an airborne disease, the mass elephant die-off in Botswana, and why sampling sewage might be a sensitive way to search for coronavirus outbreaks.
The Naked Scientists podcast is powered by ukfast.co.uk.
You might be forgiven for being slightly baffled this week with the news that airborne transmission of coronavirus and the efforts by over 200 scientists to get the World Health Organization to change its advice. If you remember a few weeks ago, we reminded you of the old phrase, coughs and sneezes spread diseases, the catchy phrase that was part of a British public health campaign dating back to the 1940s, and is still very relevant today, especially with COVID wafting around.
And with recent analyses from the Office for National Statistics suggesting that more than half of cases of coronavirus infection might be asymptomatic, those 200 scientists say we need to up our game, because someone with no symptoms can nevertheless still pass on coronavirus in small respiratory droplets when they breathe out. This is known as aerosol or airborne spread, and that's why the scientists are urging the WHO to put more emphasis on this route of transmission. Engineering professor Shelley Miller is one of them.
We wrote an open letter to the World Health Organization to get them to accept that this disease can be transmitted by inhalation of small airborne particles containing virus. And we wanted them to really consider and acknowledge this transmission route because we have been struggling with incomplete messaging across the world.
Now, when you say we, how many people were involved in this?
Initially, there were 36 scientists who came together in March, and we wrote a letter to the WHO, and they read the letter, and we had conference calls with them, and they said they would review the science, which they did, and they did not change their position. So then we wrote a paper, which was published in last month. And then finally, we took our letter and got over 200 additional scientists to sign it and publish it openly to the world so that they would know what conversations we were trying to have with WHO.
What did the WHO say when they got your letter?
Well, they wanted to talk with us again, and we have a call scheduled with them again. They just put out a statement yesterday that I have interpreted as meaning they are re-looking at the data and reconsidering our request, and then they want to also have a conversation to further the discussion. We were all thrilled, and I was just moved to tears.
And so prior to your analysis, what was the view then about what the main route of transmission was and what the risks were?
Well, from the WHO, their main position was that you could only get it from an aerosol if you were in an aerosolization procedure room in the hospital. Otherwise, if somebody coughed or sneezed near you, you could be sprayed with the droplets, or the droplets would be transferred by touching different surfaces, and then you would touch the surface and get infected. From my read with the Public Health Service in the UK and also with CDC, they have more readily embraced the idea that you can also inhale small respiratory particles that are floating in the air for long periods of time. You don't have any idea where they came from, just somebody talking, laughing, or singing expelled them, and now you inhale them and can get also sick.
Is it all part of a spectrum then? When I talk, I breathe, shout, sing, yell, all these sorts of things, I produce a range of particle sizes of droplets coming from my airways, and previously people were obsessing about the really big ones, but you're saying because there's a spectrum of droplet sizes there are some small ones, and the small ones play an equally important part in the transmission.
Yes, that's a wonderful way of putting it. That's exactly right.
And why could this possibly have been neglected before then? I'm baffled.
Yes, me too. We know many diseases are transmitted only by the aerosol route. That includes measles and chickenpox. Flu is transmitted this way as well. After SARS-1, when we had that outbreak in Hong Kong, we've found lots of evidence that that was also spread via the airborne route. And so then now we come to COVID-2, and we just are baffled by why that is not also a possibility.
At the moment, we are very busy making workplaces so-called COVID safe. And this means keeping people a certain distance apart, lots of sticky tape. The people who make stripy black and yellow sticky tape are making a fortune at the moment as we decorate the floor with it. So we've got specific routes for people to take around buildings and so on. But if people are spraying out sprays of these fine particles that can linger in the air for absolutely ages, does that make a lot of these efforts amount to really nothing? Because if you've got a nice aircon unit buzzing away in the corner of the room circulating all the air, is that not just mixing all this up and we're going to get exposed anyway, regardless of how far we stand from each other?
The actions that we have been taking are key, but we need to add a few more on top of that to address this additional risk. The farther away you get from a person that's the source of the infection, the more you reduce your possibility of exposure. But also, how do you make sure the air in your building is clean? If all you have is a recirculating air conditioning unit, then what you should also consider is adding an air purifier. That would be a great way to clean the air in the room from suspended particles that may linger.
And the best air purifier, of course, at the moment, while the weather's good, is the window. So keep the windows and doors open too. That was Shelley Miller. She is at the University of Colorado, Boulder.
Now, you've probably heard of tracking the coronavirus by swab or by app. But what about by sewage? That's the delightful proposal from scientists who want to figure out how many people are infected in, for example, a city, based on the amount of virus those people have flushed away in their waste.
Now, it's an unpleasant but promising new weapon in the corona hunting arsenal. And in theory, you can test sewage water in the same way that we test saliva, although don't muddle up the test sticks. And this is by using a technique called qPCR to look for the virus's genetic code. It's RNA. Andrew Singer at the Centre of Ecology and Hydrology is helping to lead this project, and Phil Sansom heard from him about the samples that are being provided by water companies from their treatment plants.
They provide, a liter worth of the sewage. We're effectively going to concentrate the RNA from the sample, and that goes into the qPCR, which is to quantify the amount of RNA that is present. That is the shortest version of the pipeline that we're going to be using.
That's a much better reaction than most people would have if you gave them a liter of sewage.
Well, it's amazing how much information is embedded in our wastewater.
How much can you get out of that amount of sewage, a liter of sewage?
The amount of virus that would be shed by a person might be in the hundreds of millions of virus particles per gram of feces and millions per liter of water. What we're trying to understand is what is the limits of the detection? How few people in any one population can you detect? There are some sewage works where you have only a couple of hundred people. And so it might be that one person is infected and you could see them. But one person in a sewage works of 200,000 people is probably going to be in the noise.
What are the things that are complicated when you're trying to figure out how many infected people equals how much coronavirus in the sewage?
The numbers of things that complicate this seem to have no end at the moment. What we'd love to be able to do is have confidence about the direction to travel, that there are fewer cases, or is it stable, or is it going up? It's obviously more helpful if you can then put numbers on that. And the real strength of this approach, the Holy Grail, you want to be able to say that there's 100 people in this catchment who appear to be shedding the virus, and traditional surveillance can only account for 75 of those 100, which means that there's 25 people who don't know that they're infected, but they're shedding the virus. And so having the asymptomatic shedders included in your sample gives you the power of knowing the size of the beast, so to speak.
How far away are you from that holy grail of finding out the actual quantitative numbers?
Well, we're definitely going to be having a go at it. It's a very difficult challenge to overcome. There's a number of different factors that can affect the shedding rate, and all of that will be important to feed into the model for then making better estimates.
In the meantime, right, you're planning this huge operation to do this kind of testing at every sewage plant across the UK?
So even in the national scale surveillance, which is being run by the government, they'll only be sampling 50 to 100 different sewage works because logistically, it's not going to be possible to sample the 9,000 sewage works that are within the UK. So we have to take this sort of triage, canary in the coal mine approach of saying, well, where do we think would give us the best information about COVID and also the likelihood of it transmitting to another area of the UK? So maybe commuter populations would be a really interesting place to be sampling.
How useful is sewage for that? Because when I think about the coronavirus, I think about coughing it out. I don't, excuse me for this, necessarily think about pooing it out.
I would imagine virtually no one does. There's a lot of infectious disease in poo, which is why we have the problems that we do in the world with sanitation. And then you have coronavirus, which you would not predict is going to be persistent in wastewater. But the reality is that it is.
Well, coughs and sneezes spread diseases. We said that. Diarrhea does too. Andrew Singer there. And given what we've just been hearing about, just a subtle reminder, to help the spread of coronavirus be stopped, always better to shut the lid after you flush.
Hello, sorry to butt in. Katie here from the Naked Scientists. Did you know we make other naked shows too?
The fraction of all humanity who has actually gotten a chance to see their own brain is very tiny, and you are welcomed to that club.
So if you enjoy musing over the mind, reflecting on thought, or frankly feel bamboozled by the brain, check out Naked Neuroscience.
Well, my face hurts now, so yeah, let's go. It's spicy.
Don't go down into the creepy cellar and turn the light on.
Exactly.
Access the full archive via nakedscientist.com/neuroscience or subscribe to Naked Neuroscience wherever you get your podcasts.
You're here with the Naked Scientists. Coming up, how to drive a Mars rover. You might have seen some shocking images lately from the Okavango Delta in Botswana, and these have been published all over the world. They show hundreds of dead elephants with bloated bodies lying next to waterholes. It's been described as a conservation disaster, but precisely why the elephants have died isn't fully understood. Niall McCann is the Conservation Director of National Park Rescue.
The great concern that I have is that we still do not know what this is. So we have no way of knowing whether it's going to spill over into the human population in the same way as COVID-19 did, or if it's a poison that could poison the waterways and again have a negative impact on the human population, or if it's something that we can control within the elephant population. Because there's a very real risk if this continues to run its course that Botswana's entire elephant herd could be decimated.
Do we have any theories of what it might be, or how are we going to find out?
There are three main possibilities of what it can be. The least likely is that this is a natural toxin, something like anthrax or a blue-green alga. And the reason I say that that's the least likely is because if it was any of those things, we'd be expecting to see many other species also succumbing as well. The second thing it could be, which is highly likely, is that this is a pathogen of some form, a disease which is solely confined to the elephant population and is having a very rapid impact on them. And some of them are dying very quickly. It's obviously affecting their central nervous system, whatever this is, because they're animals that are alive are being seen with motor impairments. Other animals that have died falling directly on their faces as if they're succumbing incredibly quickly. And then the third, much more sinister possibility is that this is a poison, purposefully lain either by poachers or by local farmers. There's very strong incentives for poachers to be killing large numbers of elephants because elephants carry tusks of ivory. Ivory is still worth $700 a kilo on the black market. But then also farmers in that area have a very fractious relationship with elephants, as farmers do anywhere that live next to elephants. Elephants are massively destructive. And there's a possibility that shouldn't be ruled out yet, that this was in some way a retributive act to try and protect the crop from elephant herds. But until we've got the results back, all of it's just speculation.
Is there anything else that can be done while we're waiting for the tests to keep maybe other elephants and the people near them safe?
What the Botswana government are doing is finding as many of the carcasses as they possibly can, and those that are close to human habitation are being destroyed. So they're being burned and buried so that there's no prospect of something in the blood or the tissue of that elephant getting into local livestock or into the people. But if this is something that's in the water, then it's already potentially going to cause a knock-on really negative impact on the human population. What the government are also doing is trying to defend that area from opportunistic criminals, because if you've got 400 elephants lying dead in the Okavango Delta, that's 800 tusks lying around. And now that they've been dead for a few weeks, you can walk up to those carcasses and just pull the tusks out of their face. You don't need a chainsaw or an axe to get rid of them, to get them out at this stage. So the Botswana governments are also protecting those carcasses. And I think that's really important. And it's a big area. So I think it's very important that they protect them. In terms of the public, what the public can do is just make sure that this stays in the public space. So retweet and share articles, read all the articles they possibly can, and make sure it stays in the public space so that there's no hiding. We've got to make sure that this doesn't go away. This is a public interest story of international concern. The story has gone right around the globe in the last 7 days. And I think it's really important that the government of Botswana realise that this matters to everyone. This goes way beyond the borders of Botswana. This matters to everyone, that it's resolved as quickly as possible.
And for the elephants, you said there's about 400-ish that we know are gone now. On the scale of the remaining population, how big is that loss to the species?
In terms of across the whole of Africa, we have already lost 1,000th of the remaining elephants in Africa already in this single event. Botswana has in the region of 130 to 150,000 elephants, give or take, and this region has about 15,000. So if this thing, whatever it is, continues to rip through that population in the Okavango Delta, and if it destroys that population, the Botswana herd, the largest herd left on the continent, could be decimated. And that's of significant international concern as well. This is concerning in so many ways. It's potentially a public health crisis. It's already a conservation crisis, but it's also an emotional crisis. Elephants are highly intelligent, highly sociable, very strong family bonds. Their brain is 4 times the size of ours. They cry salt tears. They mourn their dead. This must be having an absolutely massive effect on the psychology of the elephants that are surviving, watching so many of their friends and families dying. And I can only imagine that the trauma of this event is going to last for years, if not generations.
I don't know, but if you're anything like me, I've been hit pretty hard by that story. I found that one really harrowing, so I think it's important to get out there. Niall McCann on the recent elephant deaths in Botswana.
To space now, and astronomers have discovered what looks like the skeleton of a giant planet, one that should be a gas giant like Jupiter, but with all of its gas lost into space. Using a number of telescopes, the international team peered hundreds of light years out into space. Their discovery has the catchy name of TOI 849b, and it's probably made of rocks that are quite similar to the Earth. But it's 40 times larger, making it the biggest terrestrial planet that's ever been found. Phil Sanson heard about it from Warwick University's David Armstrong.
We've discovered the most massive terrestrial planet that's been found to date. It's the most massive rocky planet by a long way.
When you say terrestrial, what do you mean? Is that's not Earth out there?
No, it's not like Earth, but it does have a density very similar to Earth's, which means we think it's composed of similar materials like rocks and heavy elements.
How far away is it? Where in the sky?
It's in the Fornax constellation in the southern hemisphere, so us in the UK won't be able to see it in the night sky, but it's about 730 light years away from Earth. We detected it with the NASA TESS mission, which is observing lots of stars trying to look for periodic small dips in light as planets pass between us and the stars.
Now, if all you can tell about it is that it's making the star it goes in front of a little bit dimmer, how can you tell any of this stuff about it being rocky?
Well, in terms of how much dimmer it makes the star, that can lead us to work out how big the planet is, because the bigger the planet is, the more of the starlight it blocks. But that doesn't tell us the composition. We have to follow it up with other instruments to try and work out how massive the planet is. The primary one is the HARP spectrograph, which is at the La Silla Observatory in Chile. So that measures the star and takes its light and spreads it out into lots of different colours, the wavelengths we call them. And in those colours, there's a very specific signature that's unique to the star. If we take multiple images like that and look at these signatures and how they shift over time, we can see it shift back and forward.
What do you mean that the colours shift?
And much like an ambulance going past you, if you hear the siren pitch change when it comes towards you and moves away from you, the starlight does the same thing as it moves towards and away from us. Now, this isn't moving very fast, and so the speed is really something like a brisk walking pace, but because of modern techniques and instruments, we're still able to detect that.
That's unbelievable. So you can tell these small differences in how the star itself is moving towards and away from us. But how does that tell you about the planet?
Because much like planets orbit stars, the star actually orbits something called the centre of mass of the system, which is really located close to the centre of the star, but just a little bit towards the planet. Both of them orbit each other, rather than one orbiting the star only. The more massive the planet is, the faster the star moves, and we can connect those things and work out, once we know the mass of the star through other techniques, how massive the planet is.
Oh, interesting. So you're checking out the impact of the planet's own gravity on the star.
Yes, that's right. So once we've got the radius or size of the planet as well as its mass, that lets us work out its density.
And you said it was the biggest rocky planet that you'd ever seen. How much bigger than the Earth?
Well, most massive. It's 40 times more massive than the Earth. It's about 3.5 times the Earth's radius.
Do you have theories about what it's doing there, how it got to be so big?
To get a heavy element planet this size is very difficult. Normally when these cores are forming, once they pass a critical mass, usually around 10 times the mass of the Earth, we expect them to start building up lots and lots of hydrogen and helium very quickly. So it's actually very hard to make a planet this dense without building up lots of light gases like that and turning into something like Jupiter. One option is that this used to be a planet much like Jupiter and lost all of its outer gases to become the planet we see today. There are a few ways that could happen. I mean, maybe it collided with another forming planet quite late in its formation, and that can blow away the remnant atmosphere and leave behind a dense core like we see. Another way could be if it interacted with its host star very violently in something called tidal disruption, where the tidal forces between the planet and the star build up energy in the planet's atmosphere, and that causes it to sort of blow away and just leave the core behind.
Either way, it sounds like something really violent must have happened to leave this huge either shell or weird anomaly.
Yeah, that's true. I mean, the other more gentle option, if you will, is that the planet just got stuck while it was forming, and rather than building up all of the hydrogen and helium that we expect, just somehow managed to avoid that.
Hypothetically, if you could get me there, do you think would I be able to stand on it? Would the gravity crush me?
The gravity would crush you and the temperature would incinerate you pretty rapidly as well. This planet orbits its host star in only 18 hours, so the temperature is thousands of degrees.
What did you say it was called?
TOI 849b.
Oh my god, TOI 849b.
Yes, not the most exciting name, I appreciate.
Okay, I'll memorize that on my list of destinations not to go to.
That or bring along a pressure suit and some very powerful sunscreen. David Armstrong there, and that study has just come out in the journal Nature.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for your audio and video productions.
It's The Naked Scientists, and this week it is a tale of two planets, Mars versus Venus. And the reason we're doing this is because if all goes according to plan, pretty soon NASA will be sending a new rover called Perseverance to Mars, and the United Arab Emirates will be sending the Emirates Mars mission, which will aim to study the Martian atmosphere, weather, seasons and climate. As well as that, the European Space Agency and China also have Mars missions in the works. We'll also soon get to take a closer look at Venus when the Bepi Colombo probe buzzes by. They're two quite similar planets, but ones on which the conditions couldn't be more different. And we can learn a lot about our own planet by studying them.
Now, Venus is our closest planetary neighbour, Between 40 million and 260 million kilometres separate us, a snip in space terms, and that depends on where they are in our orbit, where we are in our orbits, of course. And this proximity is one reason why Venus is amongst the brightest of the stars in the night sky. But closeness doesn't mean this place is anything like the Earth. Eva Higginbotham has your Venusian quickfire science.
Venus is the first of our neighbours that we'll be meeting. Named for the Roman goddess of love, Venus is anything but a lovely place to be. Venus is roughly the same size as Earth, and like Earth, is a rocky planet, but that's about where the similarities end. On the Venusian surface, the temperature is hot enough to melt lead, reaching nearly 500 degrees centigrade. There is snow on the mountains of Venus, but that snow is made of metal. Venus is stuck in a runaway greenhouse effect, where the atmosphere lets heat in but doesn't let heat out. That means that despite not being as close to the Sun as Mercury, it is still the hottest planet in the solar system. If you were to stand on the surface of Venus, and you could somehow withstand the heat, you wouldn't stand the pressure. The pressure at ground level is roughly 90 times the pressure on Earth, like being 1 kilometre underwater. All that strangeness is enough for scientists to want to go and have a look, although the extreme conditions mean that most missions have not landed on the surface. But more than that, Venus might hold some information about what might happen to Earth if climate change is left completely unchecked.
So beautiful, but deadly, and maybe not the nicest place in our solar system. Now, we know a lot of this, of course, because missions like the Venus Express probe, which operated between 2005 and 2014, have been dispatched there to study the planet. So what have they discovered, and what new questions have they raised about our celestial near neighbour, where it also, as if molten metal snow wasn't floating your boat sufficiently, rains sulfuric acid?
If Venus is such a hostile place, how do you go about visiting it? How do you peer through all that thick, heavy atmosphere and actually look at the surface? Well, a few missions have been to Venus, and Professor Andrew Coates from University College London, who has worked on a few of them, took me through some of those missions.
I worked on a mission to Venus a few years ago, which was Venus Express. So this was the European Space Agency's mission to unveil some of the secrets of Venus which had been left from previous missions. Russian missions would be aimed to land on the surface, probes to go down into the atmosphere. Also, an American mission mapped the surface in great detail with radar. That was the Magellan mission. So Venus Express actually was done to try to look down towards the surface and to the lower atmosphere in particular, using windows in the infrared, which had been discovered when Galileo, actually the spacecraft on its way to Jupiter, when that passed Venus on one of its gravity assists. If you approach Venus on a spacecraft, you see these clouds, V-shaped or chevron-shaped clouds, really, associated with the planet rotating very slowly, but the atmosphere rotating very quickly. There's something called superrotation going on in the atmosphere. And so that was another thing which Venus Express was to look at. So Venus Express, European Space Agency mission, the instrument we worked on was to look at the solar-wind interaction.
And what kind of things did the Venus Express learn about the Venusian atmosphere?
Well, we knew already that Venus has a very thick atmosphere, so it's a mainly carbon dioxide atmosphere. One reason we wonder about why the atmosphere is so thick, it's a bit of a conundrum, because actually, like Mars, Venus lacks a magnetic field, and yet you've got this very thick atmosphere, despite the fact the solar wind is stripping away the top of the atmosphere all the time. So one of the things we're able to look at is how much, the rate at which material is being lost from the top of the atmosphere of Venus. And it turns out to be about the same as Mars, per unit area. So you have the same process going on in terms of losing material. You have this carbon dioxide rich atmosphere. So one of the conundrums at Venus is how comes the atmosphere is so thick now? How is this being replenished? Because over billions of years, you might expect that atmosphere to basically disappear. So one of the possibilities with Venus is there's active volcanism going on. Nobody has seen that, or nobody had seen it before Venus Express, because that window in the infrared hadn't been used to be able to look down towards the Venus surface.
It's intriguing to think what we know and what we've learned, isn't it? That was Andrew Coates. He'll be back a bit later on with more insights. So it does appear to be quite a mystery, doesn't it? How does Venus work then? Well, with us is David Rothery. He's Professor of Planetary Geoscience at the Open University. David, we seem to have some kind of contradiction here. Venus has got this crushing atmosphere, while Mars has the vague vestiges of one. They're roughly similar sort of sizes. Why the difference, do we think?
Well, the most important contrast is really between Venus and the Earth, because they really are the same size and mass. Mars is considerably smaller. What's happened on Venus with such a dense atmosphere is that all the limestone that's on the Earth as rock with carbon dioxide locked up in it doesn't exist on Venus. That carbon dioxide is all in the atmosphere. So if you add the carbon on Earth and the carbon on Venus up, they're pretty much balanced, but it's all in the atmosphere on Venus. So it's got this atmosphere 90 times the Earth's surface pressure made of carbon dioxide, and that's what gives it the greenhouse effect, which currently keeps it so hot. Mars is a much smaller body and it's lost most of its original gases.
Andrew Coates was saying that the atmosphere is being stripped away from Venus by the solar wind rather quickly. He cited the reason as it doesn't have a magnetic field. But where's the CO2 coming from then to replace that which is being blown away continuously?
Well, I think Andrew's right that Venus is losing atmosphere. I'm not sure we've got a good measure of its rate. It doesn't have a magnetic field, which is a surprise. It should have a core like the Earth's, but maybe its slow rotation is not stirring the core up to generate a magnetic field, so it's not protected from the solar wind. But the stripping away has to compete against the planet's gravity, and CO2 is quite a heavy molecule, and there's plenty of it there. So I don't think Venus is going to lose its atmosphere quickly. It's in that state for a long time and has been like that as far back in time as we can peer, which is not all that far because Venus's surface is geologically active. It doesn't have a long cratering record because it's been resurfaced by lava so many times.
Allegedly, it has the most volcanoes in the solar system.
Well, we don't know how many are active today. We don't know that any are active today. If you want somewhere that's volcanically active, you go to Jupiter's moon Io, which has got 30 or more erupting at any one time, pretty much the same number as on the Earth, but it's much smaller. We don't know if Venus is erupting today. It probably is. There have been hints, localized traces of sulfur dioxide, occasional glimpses of a little bit of localized heat through the clouds, but we don't know. That's why we need a mission dedicated to Venus. The current probe, Akatsuki, that's orbiting Venus, doesn't see down to the surface. When Bepi Colombo, the European Mercury-bound spacecraft, has a flyby of Venus in October, it won't see to the surface, but it will get some atmospheric measurements as it whizzes by.
David, you've already put your claim in for the next mission to Venus. David Rothery, don't go away. David's with us for the rest of the programme. We'll be returning to him a bit later on.
We're going to switch our attention now to Mars, which is our other close cosmic neighbour. At our nearest, it's about 50 million kilometres away and sometimes as far as 400 million kilometres away. Here's Eva with the quickfire science on the red planet.
Mars is on the opposite side of Earth to Venus and is a very different place to be. Mars is named for the Roman god of war. It has two moons, Phobos and Deimos, the Greek personifications of fear and terror, and the sons of the Greek god of war, Ares. It's known as the red planet because of the thin layer of iron oxide, or rust, coating the surface. However, despite its belligerent namesake, in a lot of ways Mars is a calmer place than Venus. It's quite small, the second smallest planet in our solar system, next to Mercury. The atmosphere on Mars is very thin, about 1% of what it is here. This might be because, unlike Earth, Mars doesn't have a magnetic field to keep the atmosphere. There is ice at the poles of Mars, just like at the poles of Earth, and it's believed that at one point Mars had liquid water on its surface and may have had the conditions to hold life. What happened to turn it into the red planet is still not fully understood, but scientists have been sending craft to visit Mars since the 60s, trying to get a better understanding of our rusty neighbour.
Never heard it described that way before. But Mars's disposition does mean that it is a bit more welcoming to land things on compared with Venus that we were talking about just now. And as a result, there have been quite a few forays there already, and some very exciting new ventures are in the offing.
We've heard from Andrew Coates from University College London already about some of the work he's done on Venus. But what about the work he's done on Mars?
Okay, so I've been lucky enough to work on a couple of Mars missions. So Mars Express, which went to Mars, launched in 2003, and we were involved in the Aspera 3 instrument, which was looking at the solar wind interaction with Mars and how the atmosphere of Mars is stripped away. For me, the most exciting mission going to Mars is the ExoMars, or Rosalind Franklin, as it's now called, rover. So it's named after the DNA pioneer, and the clue is in that because we're looking for biomarkers, basically signs of life underneath the surface of Mars. So the really new thing that that mission is going to do is to drill up to 2 meters underneath the Mars surface. That's the first time that that's been done. So the reason that's important is to get below, the surface of Mars is really harsh for life now. 3.8 billion years ago, we think it was very different, and we think there were the right opportunities for developing life there at about the same time life was developing on Earth. But now, Mars basically, 3.8 billion years ago lost its magnetic field. It's been losing its atmosphere ever since. So it's now got a very thin atmosphere, about 1% of the Earth's atmospheric pressure. So that means that the surface is basically bathed in ultraviolet. So it's a little bit like being underneath the ozone hole on Earth, a very deep ozone hole without the protection of a thick atmosphere. So that really is very harmful for life or anything to do with it. So you've got to get below where the ultraviolet can get to, so that's about 1 millimeter. Also, there's oxidization has been found on the surface, so getting below that, which is about 1 meter below the surface, and then getting below where cosmic radiation can get to. So this is radiation from the galaxy and from the sun. These are energetic particles which can get through the thick atmosphere and provide a significant radiation environment on the surface of Mars. So you have to get below that to be able to look for signs of life. So that's why we have ExoMars Rosalind Franklin being able to drill 2 meters. So the idea is to get a sample from underneath the surface, from up to 2 meters underneath the surface, underneath all that nasty stuff. So it's a pristine sample from underneath the surface, to analyze that on board the rover and then send the results back to Earth. So with all that, we hope that this mission is the most likely to actually find life signs on Mars.
It's amazingly exciting, isn't it? Andrew Coates there talking about the Rosalind Franklin ExoMars rover that is currently scheduled to launch in 2022. Now with us is Open University planetary geoscientist David Rothery. David, Andrew was talking about drilling down through this fairly sterile, pretty nasty crust that's been basted in radiation for billions of years. So they're not looking for life there, but he's saying get some sample from deeper. That's more likely to have the hallmarks of life or past life. So what sort of chemicals are they going for? What's an indicator of life?
Well, you'll look for organic molecules of various kinds. And yes, if you can drill 1 or 2 meters down, you have a better chance because the surface is very oxidized and molecules break down. But there has been a static probe, not a rover, a static probe that's attempted to drill on Mars. This is InSight, which is there recording Mars quakes. Its drill got stuck and it took a long time to get it unstuck. Drilling on a planet is tricky, which is why it's not been attempted from a rover before. But if we can do it, it's great. The NASA's mission, which is launching maybe end of July, maybe early August this year, their 2020 mission is going to be looking for organic molecules nearer the surface. It's not going to be drilling. But instruments called Raman spectrometers and the like can look at the molecules and see chemicals that were pieced together by life. You're looking at chemical fossils, because if you want to look for life, you go to places where life used to exist. The next NASA rover is going to an ancient river delta. It might be over 3 billion years old, but the sediments washed down, which may contain organic molecules. And you go to a similar environment with the Rosalind Franklin rover as well. But there you can drill a bit deeper and you stand a better chance of finding molecules that haven't been broken down in Mars's radiation harsh environment. But it is a tricky thing to do.
And two questions really, if you can cover these. One is, well, how do you know that those molecules are genuinely life and they're not just produced by natural processes? And also, how long do you think that fossil fingerprint of life could last for? In other words, what's our time window? We know that we can look at various minerals on Earth and we can say there are things trapped inside these crystals that would be a hallmark of life from 4 billion years ago on Earth. But do we know how that works on Mars?
No, we don't, to be honest, but we're hoping that these molecules can survive for 3 billion years or so. Now, they won't be unchanged. It's not like some microbe died and it's sitting there not decomposed in some way, but some of the chemicals from it last longer than others, and you're hoping to find an assemblage of chemical products, chemical fossils, which do look like they were made by life. Now, you're not going to prove life was there in the past until you've got a fossil, maybe a microfossil that you can see in a microscope on Mars. And even then people say, oh, it's just a sport of nature. It's not really a trace of life, which is why we're looking ahead to bringing bits of Mars back. And that'll be the best way to find traces of life on Mars. But it's baby steps towards the goal of demonstrating whether there was life on Mars in the past.
David, thank you. That's David Rothery. He is from the Open University.
Still to come, sending a piece of Mars back home.
Yes, you did hear that correctly, and you'll find out why. We'll be talking to the woman who's involved with that project next. But before we talk to her, the landers that we put on Mars specifically, like the car-sized Curiosity rover. Now, they need to be controlled and steered, but from Earth. Now, some say it's a bit like driving a multi-million-dollar remote-controlled car that you can't actually see over an obstacle course that you're seeing through a video camera from 250 million kilometres away. So how on earth do they do that? Well, Adam's been finding out from the world, or perhaps I should say, the Martian record holder.
If we want to learn about our neighbours, we have to send robots there to visit them. We've sent plenty of robots to trundle around the Martian surface, but how do you control them? It must be like the most high-stakes video game there is. And if it is, one man, Paolo Belluta from the Jet Propulsion Laboratory at NASA, has the high score, having driven 17 kilometres on the Martian surface, which is a world record. He told me a little bit more about how you actually control a rover.
So we receive images from the rovers and we analyze the terrain around the rover and decide together with the geologists the next destination for the rover. And then we prepare a list of commands such as move forward by a certain distance, turn by a certain amount. And we prepare this list of commands. They're supposed to be executed in a single day on Mars that we call Sol. Then we send all these commands in one chunk. The rover receives these commands and executes the commands in total autonomy.
Imagine just seeing one single snapshot of a level in Call of Duty, then having to input every command to beat that level, then going to bed and seeing what happens in the morning.
It's not easy because the only thing that we have are basically images. There are stereo images, so we can determine the distance, the size of the obstacles that we see in the images. Also, we have a geologist that can help us in determining whether the terrain that we plan to move, the vehicle, is safe in the sense that it can support the weight of the vehicle, or if the obstacles might be too dangerous for the vehicle.
So if you're a pro like Paolo, you know what you're doing, and you don't crash a very expensive NASA rover. But how have things changed since the early days?
I started driving vehicles on Mars in 2004, and at that time it was quite rudimentary, I would say. Not only because the vehicles at that time, they were smaller, but also the software on board was pretty simple, but mostly because we didn't know how to drive on Mars.
And what's it like to play what you might call a real-life space invader?
The best part of my work is that it is never boring. It is always new. There is new problems every day to solve, and therefore it is always exciting. There hasn't been a boring day on Mars.
Paolo Belluta from JPL there.
Now, if all goes well, NASA is soon going to be sending a new rover. It's called Perseverance to Mars as well. This is also car-sized. It weighs about a ton. It's powered by a plutonium thermoelectric generator, and it even has its own drone. This is like a super yacht with a helicopter on the back. This one's called the Mars helicopter, and it's going to be there to test the feasibility of flight on Mars. Now, like the Rosalind Franklin ExoMars rover that we were talking about briefly earlier, the overall mission is to seek out signs of ancient life. And also it's going to collect and store rock and soil samples for return to the Earth in the future, possibly. But also aboard is something a bit special and quite unusual. It's going to be taking with it a little piece of Mars that landed here in the past. And to explain why on earth, if that's the right phrase, they're doing that, is Caroline Smith. She's the principal curator of meteorites at the Natural History Museum in London. Caroline, please put me out of my misery. Why on earth are you sending a bit of Mars back to Mars?
I know, it sounds a bit strange, doesn't it? Well, it's actually a really interesting piece of scientific research we're doing that's actually going to be very important for one of the instruments that I'm actually involved with, which is called Sherlock. And what we've actually done is we've taken a small piece of one of our Martian meteorites, which has a name in Arabic, so you'll have to forgive my bad pronunciation, but it's Saya al-Yuhamir 008, or we call it SAU 008. Yes, exactly. You have to sort of think about saying it. And it was found in Oman in 1999. And the reason why we've selected it is that it's actually on something called the calibration target for the Sherlock instrument. And so what that does is when the instrument is operating on Mars, so doing the analyses of different rocks and different minerals within those rocks, but also really importantly, Sherlock is looking for the presence of organic molecules. What you can actually do is before you use the instrument to do an analysis on Mars, you actually test how the instrument is working using the calibration target. And there are other pieces of material and other things on the calibration target, but the Martian meteorite is one of the things on there.
Caroline, it may sound like an obvious question, but how do you know that the meteorite you have sitting there from Oman is from Mars at all?
Oh, it's a great question, but it says to us, to a geochemist, it says Mars, it has Mars written through it like a stick of Blackpool rock has Blackpool written through it. So it's got lots of different chemical signatures in its makeup, in its minerals, that show that it has to be from Mars. So there was lots of pieces of evidence pointing towards these meteorites being from Mars, but it was only in the mid-1980s that it was conclusively proven that this type of meteorite was from Mars. And that was done by being able to detect tiny amounts of trapped gases in the minerals, and those gases get trapped in the minerals, in the rock, as that rock is actually cooling, because it's a volcanic rock, it's an igneous rock. And we were able to take out or measure those tiny amounts of gas using very sophisticated instruments. And when the composition of the gas was compared to the composition of the Martian atmosphere, and we know what Mars's atmosphere is from, originally from the Viking landers, they didn't move around, they just landed in the late 1970s, and there's been further experiments since on different rovers and different missions. We know exactly what Mars's atmosphere is like, and the little bits of trapped gas within these meteorites have got exactly the same composition as the Martian atmosphere. So that says to us that is, there's nowhere else that those rocks can be from. They have to be from Mars.
Why can't you do this calibration of the instrument here and just send it calibrated?
Well, we can, and we do, and a lot of work has been done by my colleagues at JPL who have designed and built this instrument to do exactly that. So JPL actually have a mirror copy of the instrument in the lab over in Pasadena, and they also have a small piece of the meteorite over there to test the lab-based instrument. But it's good scientific method when you're doing analyses. You want to be measuring the calibration target, the standard material, every time that you do an analysis to make sure that your instrument is working as you expect it, so you can be confident that the data you receive back from the rover of the Martian material that it's measuring as it's roving around Mars is actually good data and sending you back reliable and accurate numbers.
And how have you picked where you're going to sample, and what are you actually going to measure?
It's a very complicated thing. So we know where we're going on Mars now. It's a place called Jezero Crater. It has lots of different rock types, but importantly, it has rock types that we think could well have been laid down in water or altered by water. And water is a very important thing that you need for life. So if you've had water somewhere, that's a good indicator that you could have had the conditions for life. The rover has a number of different pieces of payload, so different scientific instruments on there to measure different things. And so you're looking for different rock types, their textures, their sort of physical form, and you look at the chemistry and you use the different instruments to have a look at the different minerals that are there, the shapes that are there, the different chemistry of those different minerals to see what's what. So that's what we'll be doing. We'll be using Sherlock in combination with a number of other instruments on the rover to actually really try and get a good idea of what those rocks are and do they show any evidence for potential past life, or the evidence that maybe the right chemistry, the right environment was there for past life.
I mentioned when we began talking that one of the aspirations of Perseverance, the rover, is that it will collect some samples and store them for possible later retrieval back to Earth. How on earth are you going to get them back?
Well, it's a very challenging scientific and engineering thing to do, actually. It's going to be one of the most complicated missions since the Apollo missions in the late 60s and early 70s. So it's a multi-phase mission. It's an international campaign. We actually call it the Mars Sample Return Campaign, and it's being done jointly between NASA and the European Space Agency. And so there will be different missions sent subsequent to Perseverance collecting the samples, and then the last one of those will actually blast those samples off the surface of Mars. The samples will be collected in another satellite, for want of a better word, that's been orbiting from Mars, waiting for those samples to be delivered to it up in space, and then hopefully we'll be able to safely get those samples back on Earth in around maybe 2031, 2030-ish. That's the sort of timeline we're looking at. So, 10, 11 years from now, we'll hopefully get these really precious, amazing samples back, because we can only answer these questions once we get the samples back on Earth.
Brilliantly done. Caroline Smith, no relation to me. There's not many of us around. Easy mistake to make.
No,
She's at the Natural History Museum in London. Thanks very much, and thanks to our other guests this week, Andrew Coates, David Rothery and Paolo Belluta.
And we've just got time for Question of the Week, where Eva Higginbotham's been scrubbing up to answer this question from Carol.
The government has provided more than 1 billion items of PPE to hospitals. There have been 130,000 COVID cases in hospitals, about 10,000 items of PPE per patient. Can you find out why so much?
Let me just pop my gloves on. Now, let's have a look at those numbers, shall we? Between the 25th of February and the 5th of July 2020, the government provided 2.2 billion items of PPE, or personal protective equipment, to the NHS. That's a big number for the 280,000-ish cases of coronavirus that we've had so far. So where is it all going? I put the question to medic Isabel Cochrane.
Let's start by considering the figure itself. This 2.2 billion comprises not only the more obvious items such as masks, aprons, gowns and individual gloves, but also includes behind-the-scenes provisions such as cleaning equipment, detergent, swabs and body bags.
So the definition that the government is using for PPE is broader than you might first think. But how do the numbers scale up to nearly 10,000 items per patient?
Let's do the maths. When seeing a patient, a member of staff would be expected to wear a minimum of gloves, an apron and a mask. So at least 4 items of PPE. Usually, a visor and a hat would also be needed, increasing this to 6 items per patient encounter. Although PPE can sometimes be reused, generally, between seeing patients, you would be expected to change at the very least your gloves and gown to minimise the possibility of transmission of infection. Add to this that medical teams are pack animals. A patient in A&E might expect to be seen by a couple of junior doctors, a consultant, 1 or 2 nurses, then accompanied by 2 porters to the radiographer who takes their chest x-ray. You get the idea.
The latest government guidelines also state that staff should wear PPE when seeing any patient, not just confirmed or suspected COVID cases. And there's also the tremendous work being done by the NHS outside of hospitals in community settings. The numbers really add up.
Finally, it might be worth asking how much PPE the NHS uses on a good day. The figure for PPE provision across the NHS in the year 2019 was around 2.4 billion. So, despite the pandemic, we're only using about 3 times as much PPE as normal, a comparison which can help put numbers with lots of zeros on the end into perspective.
So there you have it. Thanks, Isabel. Next week, we'll be getting into a lather over this question from Julie.
I'm wondering if there's any science around the wash, rinse, repeat method that manufacturers tell us is the best way to use their shampoos, or is it just a really clever way of getting us to use more? Thank you.
So what do you think? You can ask via our website by going to thenakedscientist.com/question, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on the forum, thenakedscientist.com/forum.
And that is it for this week. Thanks to Adam who put the programme together, and be sure to tune in next time because we are having a DNA party to celebrate Rosalind Franklin, who we've heard a bit about in this programme. Well, it's her, or would be her, 100th birthday on the 25th of July, and we're marking the occasion. The Naked Scientist comes to you from the Institute of Continuing Education at the University of Cambridge. It's supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.